Second. Hello everybody, this is the second lecture of the Victory, and this is going to be the last lecture about the pipe flow. And today I am going to introduce you and provide some information about some specific problems. These are about the pipes in parallel or pipes in connected in series. After introducing you this topic, then I'm going to finalize the topic with, the pipe flow, with introducing you how you can measure flow in pipes and what are the calculation principles for pressure loss in flow measurement systems. So let's start with the first topic. First topic is, as I told you, if you connect pipes in series or in parallel, how you are going to calculate energy losses. So let's look at first on the left side, the connection of pipes in series. Thinking that way, you guys, you are delivering water in a city, and at the beginning of the city, the volume is going to be high because you will not deliver too much water, and you are going to select a large pipe. And when you go through the city, you are going to deliver water in branches. And the main pipeline, transmission pipeline, is going to be get smaller and smaller. This is a kind of efficient management. So, and also it's a common practice. So you can reduce the pipeline dimension when the flow rate is also reduced in the pipe through the flow. In this case, you are supposed to make some pipeline connections in series. In series, like given on the screen on the left side. Here, the type of materials are typically selected as the same material. However, it could be different, okay? Still, the pipe material even could be different. So you may assume that the friction factors are going to be different for pipe A and pipe B, and the lengths are most probably going to be different, okay? LA and LB, and diameters are also different. So it means that you should calculate a hydraulic loss for pipe A, another hydraulic loss for pipe B, then the total hydraulic loss is going to be the hydraulic loss 1 plus hydraulic loss 2, okay? So in series, you are supposed to calculate hydraulic losses for each piece of the pipe, then you are going to sum them up. This is how we are solving the problem in series, okay? In parallel pipes, it is different. It is totally different topic and the concept. And if there are two parallel pipes in one branch, thinking that way, between A and B, if there are two parallel pipes, like given on the screen, okay, on the right side, you see that pipe A is going one side and pipe B is going another side, and their lengths are totally different. One is, for example, 1,000 meters, the other one is 2,000 meters, and diameters could be different too. It means that the flow rates are going to be different. But there is one simple rule you should always remember, okay? The hydraulic losses in pipe A is going to be equal to hydraulic loss in pipe B, okay? If pipes are parallel, the hydraulic losses are going to be equal to each other. Have a look at here, okay? So hydraulic loss on pipe 1, pipe A is going to be the same amount with the hydraulic loss in pipe B, okay? This is the general description of how you can solve the problems in terms of having serial connection pipes or parallel connection pipes. Okay, do you have any question? I am going to solve one problem to make it more obvious. And if you don't have any question, we can continue with the problem. Any questions, guys? No? Good. Okay, let's have a look at the problem. This is the problem what we have. And as you see that there is a pipeline system, and in a certain part of the pipe, the pipe system, the pipe is making a branch, a kind of parallel branch, pipe branch A and branch B. And in both branches, the same parameters, same pipe is used, okay? So the pipe A is equal to pipe B, or pipe 1 is equal to pipe 2 in terms of material. It means that they have the same fraction factor. Okay, so you can use fraction factor A and B, and you can assume that they are equal to each other. And here it says that the diameters are the same. It means that if the diameters are the same and the friction factor is the same, you may assume that the same amount of energy loss can be obtained per length if the volumes are the same. However, the pipe A is smaller, shorter than pipe B, 3 times shorter. Pipe A is 100 meter, pipe B is 300 meter, 3,000 meter, 1,000 meter. It means that the flows are going to be different in each pipe. And the question is also telling us that the type of pipe is given here as cast iron piping, and also the relative roughness value is given in meter. And also let's have a look at that. The diameter is given as 30 centimeter for both, and the lengths are given. And okay, this is a crucial information. It says that the flow rate at branch A is 0.4 cubic meter per second. Okay, this is branch A. And the question is asking that what should be the flow rate on B? And also it suggests that you may disregard the minor losses. Okay, you are not going to assume that there is any minor loss. You are just going to assume that there is no minor loss. And the temperature is given, density is given, and dynamic viscosity is given here. And if it is not given, you will take sorry guys. And if it is not given, you can take density as 1,000, and you know the viscosity is 1.007. Is a typical value in terms of Pascal second. So the solution is quite simple. Let's have a look how to solve it. The first thing is that let's calculate the velocity on pipe A, because we know that what is flow rate, and we know the area, and the velocity on pipe A is going to be 5.7 meter per second. And let's have a look at the question again. The pipe is short, this pipe is long, and you know that when velocities increase, based on the Darcy-Weisbach equation, we know that if velocity is increased, the energy loss is going to be larger. So this pipe is long, and in order to keep the same amount of energy losses in both pipes, it is a theory. So energy loss at pipe A is going to be equal, it should be equal to energy loss at pipe B. So most probably, not most probably, certainly you should have a lower amount of flow rate, okay, because the dimensions are the same in pipe B. So if our flow rate and velocity, okay, and if our velocity is 5.7, by logic, you would easily say that the velocity in pipe B is going to be smaller, okay, than the velocity in pipe A. It means that the flow rate is going to be smaller than flow rate at A. So there is no way that these two pipes can carry more than 0.8 cubic meter per second. This is carrying 0.4 cubic meter per second, and the pipe B should carry less. It means that you should carry less than 0.8 cubic meter per second. Let's find it. And we calculated velocity. And in theory, as I told you that velocity, flow rates are going to be same in branch A and branch B. And if you write the equation as given on the screen, follow my cursor, you will see it. And then, yes, after writing this equation, you will see that, yes, you will see that the velocity at branch B is going to be just 3.3 meter per second. And you also saw that the velocity at branch B is, smaller than velocity at branch A. It means that a lower flow rate. And if you calculate the flow rate, you will find that it's almost half of the flow rate from branch A. So it is 0.23 cubic meter per second. However, at this point, we should also make a kind of cross-checking for our assumption. Our assumption is that the flow should be in a turbulent flow, okay? And one more thing, still we don't know what is the F value. And if you are also asked to find the F value, actually this is in this question, this is not asked for you. The problem is solved at the moment. But still, I want you to extend the solution by focusing on what would be the F value. And let's work a little bit by using the diagram of Moody chart. And it's also going to be a reminder for you for the earlier session. And let's calculate the Reynolds number. Anyway, you can use any of the pipe to make a calculation, or you can make a kind of double checking by focusing on both of the pipes. And now here I'm going to make the calculation for branch B. And for branch B, I put here density and the velocity and the diameter of the pipe. Then dynamic viscosity is also here. And you see that it is around 900,000, the Reynolds number is. And also epsilon over D value is calculated as 0.00087. And if you put everything on the Moody chart, this is the Reynolds number I calculated. And this is the epsilon value, epsilon over D value. And this is the curve of the flow. And you see that it is going to be something like F value is going to be something like 0.017. And this is the F value. And also our flow is in the region of fully turbulent zone. So it confirms that the flow is as it is supposed to be. And this is our F value. Okay, guys, any question? I think everything is clear, isn't it?
Yes, it's clear.
Yeah, if you don't have any question, okay, I'm going to finish this session, not this session, this part of the session. So the second thing today I like to talk is how you can measure the flow rates in pipelines, okay? So guys, think in that way, there is no a kind of very accurate system to measure the flow rate. And most of time in pipeline measurements, engineers prefer to use some orifice plates, okay? And you see the type of orifice plates here. These are orifice plates. And what they do basically, please have a look at this graph, okay? Please look at this graph. I'm going to throw it for you, okay? Please look at this graph. And in this graph, they are just inserting this, one of the orifice plates given here on the top, okay? One of the orifice places given here on the top. They are just inserting those, one of the orifice places in the pipeline. And then this orifice plate is somehow changing the flow because of the size. I mean, see that the diameter is getting less and it is somehow blocking the flow and you are going to lose some energy. And such a kind of equipment will allow engineers to perform some calculations in terms of energy loss or pressure loss. And then you can also estimate the flow rate in the pipeline system by using such devices. And in water engineering, this device is called orifice plates or nozzles. There is a kind of venturimeter. There is a nozzle here. Nozzle is going in like that one. Nozzle is typically a kind of narrowing pipe inserted in the other pipe, okay? And venturimeters are like this one. So this part of the equipment is a venturi. Venturi has a kind of narrow neck, and you can connect it in both sides of the pipeline. And then during the flow changing, you can also measure the flow rate changes. This is a kind of typical venturimeter. This is a typical flow nozzle, and this is a typical orifice plate. So there are different equipments that can be used to make a kind of measurement for the flow rates or velocities of the pipe flow in pipeline systems. And in theory, this is how in theory it is calculated. Let's have a look at that. What is telling us that? Again, on the right side, there are cross-section drawings of orifice meter on the top, a flow nozzle in the middle, and a venturimeter on the bottom. So these are three typical measurement system, flow rate measurement system that can be used in pipeline flows. And the principle is going on actually in that way. You are going to write a kind of Bernoulli equation in both sides, point A and point B. Point A means, or point 1 means the flow before the orifice plate, and point B means the flow after the orifice plate. And if you write a kind of Bernoulli equation like this one, they should be equal to each other. However, they are not going to be equal. There will be certain amount of energy loss here, okay? And also, You know that what velocity 1 and velocity 1, you can easily calculate them. And do not forget that there is a beta, okay? I call it beta factor. The beta factor is actually d2 over d1. It means the diameter of the downflow pipe over, the diameter of the orifice over the diameter of the pipe will give you the constant value of beta. Okay, this is important to remember that this is the beta factor, and the the flow rate can be written in this equation. And here there are some other derivatives of the equation. If it is orifice meter, this is a kind of correction factor, okay, experimental coefficient factor for energy loss. And for orifice meter, it is this. For nozzle meter, it is this. And there is no need to memorize anything. Don't worry. If I am going to give you a problem in your exams, I will provide all the equations for you. And then you should only know that, for example, what is beta here? Beta is the ratio between the diameters, okay? And then you can easily apply the equation and principles as given. And also, for example, if I give you a question like this one, okay, like a nozzle meter, definitely I'm not going to tell you that this is nozzle. You should be also able to differentiate what is an orifice meter, what is a nozzle meter, and what is a venturi meter. Okay, because you are taking a kind of hydraulic course and you pass the fluid mechanics course. I am expecting all of you to know that what is an orifice meter, flow nozzle, or a venturi meter. And then you can use a kind of generic equation. The generic equation is here. Then you can calculate the flow rate. And the equipment is used for flow rate. For example, if you buy a orifice meter from a company, and if you use it as a kind of flow meter measurement device, that company will also provide you the C value. Okay, C value is the constant value. It's a combination of CD and beta. So there is no need to know what is CD. There is no need to calculate beta. And the only thing is that you should know that the C factor, and you are going to take the C factor from the factory or from the catalog for that orifice, and you are going to calculate the area of the orifice, and then you put everything in the equation, then you can easily calculate what is the flow rate. That's why such systems are quite useful to calculate the flow rate of any pipe. And let's solve one problem, then our lecture will be over. Let me check. I think, yeah, we are going to have a little bit short lecture today. But this question is a little bit difficult to understand. It might be because we have different graphics to solve the problem. Please let me know if you do not understand. I will be very happy to repeat it if it is not clear. Okay, let's have a look at what we have. The question is telling us that a square-edged orifice. Okay, so look at this figure. Here I am showing you with my cursor. It is a square-edged orifice because the edge of the orifice is square, okay? With a radius taps is installed in a 6-inch pipe, okay? So this is the diameter of the pipe, and it is in inch and it is in meter. And also the orifice is 3-inch. So the pipe is 6-inch, orifice is 3-inch, okay? Pipe is 6-inch, orifice is 3-inch in diameter. And the question is asking us that find the flow rate when a mercury manometer connected across the tap measures 122 millimeters. It means that there is a mercury manometer here, okay? And it reads out that it is not human, okay? It is not a kind of YouTube manometer. It is just the mercury manometer. So you should know that this is the energy loss. Okay, this is the energy loss. 122 is the in millimeters. It is the energy loss. So we know the amount of energy loss in the system, and then now we will calculate what is the flow rate. Okay, just please read the question by yourself and give me 1 second to take a sip of water. Still, I am having some problems with my throat. Yeah, that COVID is a difficult disease. I mean, I have still some problems in speaking, a long time speaking anyway. Okay, are you ready? Can we solve? And guys, in order to solve such problem, I just found for you a kind of typical catalog information for one orifice, and I collected this information from Crenco, okay? And some other details about the Crenco and their products are given in the link. If you use this link on the bottom, you can find the similar graphs and the characteristics of the orifice. So you need such a kind of graph to solve the problems as given. And here, let's have a look at that. What we have, there are two graphs. Actually, these are the same graph, okay? But these are the same graph. But here, this graph is drawn by using Reynolds number on the y-axis and C value on the x-axis. But here, there's a third parameter. It is beta. It shows us the beta factor. Okay, beta versus C. So if you can calculate the beta factor like D2 or D1, then you can easily find. Okay, you can easily find the curve of the pipe. And then from that curve of the pipe, you can estimate the C value by using the Reynolds. Alternatively here, this is much better graph and might be very easy because see that graph, I mean, the lines are quite smooth and almost a linear line. So if we have still Reynolds number here, you can calculate the Reynolds number, but it is based on D2, but this is based on D1, okay? Because we have different flows. This is a kind of flow giving us the values for D2, and this is the values given for D1, and we have two different flows. And in this case, if you use the pipe diameter, it might be more logical to use this figure, but still you can use orifice diameter to make a calculation for this. Anyway, let's continue. And also C value is given as a kind of equation is given here. Anyway, we are not going to use it, but D2 over D1 is a beta factor. I just provided it for you here to help you to explain what's going on here. Let's continue and solve the problem. Okay, actually the solution is quite simple. Let's first calculate the beta value. It is 3 inch over 9.056 inch, and it's around 0.5, almost 0.5. Okay, so please let's have a look at here, and you will find that where is 0.5. This is 0.5. Okay, so the beta value. Okay, the curves are for beta values, and here I found this is 0.5, and it means that it is here. And I made it red for you to follow it easily. See that this red graph is our beta graph, and for D1. And then here, we also assume that flow is okay. So as I told you that the flow is supposed to be fully turbulent. And in most of the engineering design, this is what we do. And fully turbulent means that the flow should be more than 4,000, okay? So flow should be more than 4,000. So the Reynolds number, we are going to look at it only those things. And if you go up, we are only interested in this zone. We are only interested in this zone. So if you go here, you are going to see that the value could be something lower than 0.65. Okay, 0.65. It is possible to use any value which is less than 0.65, between 0.6. Okay, so you can make a kind of initial guess for C value, something between 0.6 and 65. And if you look at the other graph, oops, sorry guys. And if you look at the other graph, you will also see that, sorry, you will also see that we have the Reynolds number. We don't know the Reynolds number, but still it is going to be a kind of fully turbulent. Turbulent, it means that more than 4,000, and more than 4,000, the ratio of orifice diameter to pipe diameter, it is beta again. It is going to be somewhere here, okay? Quite a linear part. And if you go left, see that it is almost at the level of 0.62. So I can confirm that 0.62 is between 0.6 and 0.65. So I am selecting 0.62 as the C value. And when you put this C value here, okay, because our pressure difference is equal to the energy loss, what we have in the pipe. And guys, I don't know if you remember, just give me 1 second. I don't have my drawer. Sorry, my Wacom is not working, but I am going to show you. Let's go that. Let's go here first. Okay, so it says that we have a mercury manometer connected. It means, let's check it out. I think it was you should remember it well because it was a question in your final exam. So we have a mercury manometer here, okay, connected. Mercury manometer here connected. And there is a mercury here, and there is a pressure difference. It means that we have, sorry, not like that one. Sorry. It's terrible. Okay, so this is the mercury manometer we have. And the pressure will be higher here, okay? And the pressure will be lower here. And all of this place will be with mercury, but here we have water. And the difference between this, okay, like this one is equal to 122 millimeter. But here, this part is filled with water, okay, water. But this part is filled with mercury. Okay, that's why while you are calculating the pressure difference, you should use the equation accordingly based on the manometer theory. And I am pretty sure that you remember everything because it was, again, your final exam question in your fluid mechanics course. And here, let's look at, and while we are calculating pressure difference, we used here the density of mercury minus water. This is quite important. If you don't do that, you are going to make a mistake. You should subtract the density of mercury from the water. Then this is the height. You are reading on the manometer. Then you can calculate the pressure difference in terms of meter. And this is the amount of pressure loss in pressure head. 1.533 meters is the pressure head. And if you use this pressure head in the equation here, and we estimated that the C value is equal to 0.62, then you can calculate that the flow rate of this pipe is around 15.5 liters per second. And then let's check it out. If our assumption is correct, it means that if the flow is fully turbulent or not, because we assume that our flow zone should be somewhere here. Okay, we assume that our flow zone should be somewhere here or somewhere here. Okay, this was our assumption, you remember. And let's check it out if it is correct. And we put everything here in terms of velocity, diameter, density, and kinematic viscosity. Sorry, dynamic viscosity. Then we found that the flow rate is 1.25. 127,000. It is a large number. It perfectly fits here, and our assumption is correct. The flow is fully turbulent, and selection is correct. C is 0.62, and we may assume that the problem is solved correctly. So this is the correct velocity, and this is the correct flow rate. Okay, so it is your turn now, guys. This is the end of pipe flow. After this one, I'm going to finish talking about and teaching about the pipe flow. So I strongly suggest you to focus on the questions at the end chapter of Yunus Chengiz book, chapter 8. Okay, there are many questions over there, and please solve as many questions as you like. And if you are having difficulties solving any problem, you may approach me. I will be very happy to support you. And help you in solving those problems related to pipe flow only. And next week we are going to start with open channel flow. And now today pipe flow is over. I think you have learned all the fundamental information which is required in hydraulics to make any calculation for pipe flow. Okay, any questions now, please? Aslan, are you saying something?
Professor,
Yes, please, Takmina, go on.
next week, can we have tutorial to solve some more problems related to pipe flow?
Okay, let me check my timing. I am not pretty sure. We can do that, why not? Because it seems that there's something in my agenda on next week. Just give me 1 second, Takmina. And we are talking about next week, right?
Yes, next week.
Next week, our tutorial hour is it is
It's Wednesday from 3
it is
to
Wednesday. It's not in my agenda. Which hour it is? Could you please remind me?
from 3 to 3:50.
Starting at 1, right? 1 o'clock. Okay, I think we can do that. Okay, could you please remind me on Tuesday again, Takmina, if you need it, okay? And we can plan, maybe I can solve you a couple of problems, or maybe we can resolve some problems. I don't know, in tutorial, I may solve you 1 or 2 problems. Okay, I think we can do that, okay? So if it is at 1 o'clock, I'm going to check on register again. Just give me 1 second, something is wrong.
Oh, it's 3 o'clock, not 1.
3 o'clock? Oh,
Yes.
well, it is doable, so I am taking a note for tutorial. Okay. Okay, guys, we can make a kind of section and tutorial. So I can make a kind of quick recovery from start to end. It means that we can make a kind of quick recovery for pipeline flow on tutorial. Okay. And I am not going to teach. Instead of teaching, maybe I can solve you a couple of problems, or I can wait and answer your questions if you have any questions. So get ready, just review everything I told you about you, okay? And just come to me with proper questions, then I can answer. Otherwise, I am not going to make another teaching session, because tutorials are not supposed to be teaching. Rather than teaching, I am going to recover. And if you have any questions, or if you didn't understand anything, I can answer you. Maybe also I will bring you a couple of questions if I can, and we can solve those problems in that section too. Okay, great. Anyway, we are going to confirm it again on
Tuesday, right?
On Tuesday. I'm going to ask that how many people are going to join, and if there's a certain number of people, I will do that.
Okay.
Sorry, why Tuesday? We have tutorial on Wednesdays.
It is Wednesday. It is tutorial day. It is given on register. It is assigned on tutorials on Wednesdays. I mean, we didn't do that. It is just the day. Let me check again. Now I am checking on hydraulics. It is Wednesday between 5. Yeah, it is Wednesday between 5. It's 3 and 3:50. It is on the register. Check your agenda. We didn't choose it. It is already there. It should be your own calendar. Okay. Okay, guys. So if you don't have any question, I'm going to finish today's session. That's all. So it is the end of pipeline flow or pipe flow. And then we will start open channel flow on next week.
Thank you. Goodbye.
Okay. Okay. See you next week. Bye bye.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you. Goodbye, Professor.